Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.1. Areas and Riemann sums.
Lesson 3. Sigma notation for sums. So what we're going to do next is to look at a special kind of notation that helps us to write these long sums in a more efficient way. When we write out the Riemann sum, we were writing stuff like this that had lots of terms in it and had these dots in between. And as you've probably noticed, just even trying the examples in the video, it takes a long time to write a sum that way. So when we have a sum of terms that have some kind of pattern to them, there's a shorthand way to write a long sum like that. And that's what we're going to learn about next. So we'll come back to these Riemann sums at the end of this video. But first we're going to learn something called sigma notation. And sigma is the letter, the capital version of sigma looks like this. Looks sort of like, I don't know, a sideways M, I guess. It's a Greek letter. I believe it's the 18th Greek letter. The Greek alphabet has 24 characters like ours does, and it has an uppercase version and a lowercase version. This is the uppercase version of sigma. So we're going to learn about something that's referred to as sigma notation, and it's a way of writing a long sum that has a pattern to it in a condensed form. So let's look at an example to understand how sigma notation works. Suppose I have something like this. The sum 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed. We can see that there's definitely a pattern in this particular sum. It's really the numbers 1, 2, 3, 4, 5, and 6 all raised to the third power. So we could use variables to describe an arbitrary term in this sum. Each term is of the form, and I'm going to use the variable I. Each of these terms looks like I raised to the third power. So they really look like this function I cubed, where we've plugged in some values ranging from 1 to 6. So I'll say where I runs from 1, goes up by 1 each time, so 1, 2, 3, 4, 5, and ends at 6 in this case. So this particular sum, instead of writing all of these 6 terms out, can be written in a more condensed way, and that's using this Greek letter sigma. So I'm going to go ahead and kind of write down how the sigma notation works, and then we'll kind of go through it and make sure that we understand why that's equal to this sum that we were originally given. So I'm putting down sigma here, and sigma in words is going to be read the sum. So sigma, that symbol there, we will think of as representing the words the sum. And it's going to be the sum of this function, I cubed, because we saw that all of these terms looked like this function evaluated for some I value. And down below we put where we want our I to begin. Well, for this sum it begins with I equals 1. And we said it ends at I equals 6. And in words, the way we would read this little thing is we would say the sum of I cubed as I runs from 1 to 6. So that's kind of a lot to say, but I'll say it on a few different ones and you'll get used to that. Well, what exactly does this sigma notation mean? Well, this means that we evaluate the function that's inside here, I cubed in this case. We evaluate it first for I equals 1. So this thing that's down at the bottom here is called our lower limit. It's the lower limit on the sum. And the 6 that's up here is referred to as the upper limit on our sum. So this would be telling me that I'm going to evaluate I cubed starting at the lower limit, which is I equals 1. So I go ahead and I evaluate I cubed and say, oh, okay, that would be 1 to the third power. And then we go up by 1 each time until we hit the upper limit. So the next thing I would do, I always increase by 1, so I'm going to say plus 1 here. And now I evaluate this same function that's inside here, the I cubed, when I replace I with 2. So I'll get 2 cubed. And the next thing I would do is replace the I with 3, so 3 cubed, 4 cubed, 5 cubed, and then I stop at 6 because I see that there's an upper limit on my sum of 6. So I would stop at 6 cubed. And this sigma here tells us then to add all of those things together. So the sigma would say add all of these up. And then whatever sum we end up with down there would be this total sum. So the sigma tells us to then add all of those up. So it says, okay, so I'm going to do 1 cubed plus 2 cubed plus and so on until I get to the upper limit of 6. So my last term would be 6 cubed. And that's how this notation right here would mean exactly the same thing as the original example that we were given. So it takes a little bit to kind of get used to that sigma notation, but that is what it means. Just evaluate this function, starting whatever the lower limit value is, going up by 1 each time for each term until I reach the upper limit, and the sigma tells me to then add all of those terms together. So we add all of those together. And I'm not even going to bother to actually add all of those up. We just want to understand how this sum of 6 terms can be written in this sigma notation. Well, let's try it for a few other examples, and then I think you'll start to get a feel for how the sigma notation works. So let's try this one together. I'm doing the sum, I have my sigma here, from I equals 2, so that's my lower limit is 2, to I equals 5, that's my upper limit, of the function I squared. So all that means is I'm taking this function I squared and I'm evaluating it starting at the lower limit here, starting at a value of 2. So my very first term would be 2. I'm plugging it into the I squared function, so that would be 2 squared. I always go up by 1, so my next term would be 3 squared, 4 squared, 5 squared, and then I notice, oh, I'm at my upper limit, and so then I want to stop at that point. And the sigma then says take all of those terms and add them. So the sigma is saying do the sum of I squared from I equals 2 to 5. So 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, why don't you try the next two yourself? Just write out what the terms would be. Don't bother to add them up. We're just trying to understand this sigma notation. So pause the video, and then if you get stuck, just restart the video and we'll go through them together. Okay, well, let's try the second one. We're going I equals 1 to 6, the sum of I equals 1 to 6 of 1 over I. So my function in this case is 1 over whatever my I value is, and my lower limit is 1, so that tells me where to start. So I start by evaluating 1 over I, where I replace the I with 1. I always go up by 1 unit each time for the I value, so I'll do 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, but then at that point I notice I'm at my upper limit, so that tells me to stop. And the sigma letter means to go ahead and do the sum of all of those things. And in words we'd say the sum of 1 over I from I equal 1 to 6, and this is how we would write that out. For the one that's at the bottom, my lower limit is 4, so just notice that you're going to start with an I value of 4. The function that I'm evaluating is the function 3 times I. So in words we would say this is the sum of the function 3i from I equals 4 to 8. So I start with 3i means 3 times I, so I start with 3 times 4. And now I want my I to increase by 1, so the next one would be 3 times 5. 3 times 6, 3 times 7, and 3 times 8. And then the summation sign tells me to add all of those together. And I just double check, yeah, I started at the correct lower limit of 4, and I kept changing my I until I got to the correct upper limit of 8. Well, let's try a few more and just get really used to this sigma notation, and then we're going to apply it to those long sums that we talked about before. So let's look at, actually, why don't you try these three, see if you can write out what those sums are. And with the second and the third one, you might also go ahead and try to simplify at least this portion that's in front, the factor that's in front, -1 to the I, because it will simplify significantly. Well, give it a try and then restart the video when you're ready to go through it together. Okay, well, let's look at the one at the top. I'm doing the sum of 2 to the I as I runs from 0 to 5. So I want to evaluate this 2 to the I starting at the lower limit of 0. So I start by replacing the I with a 0. Then I'm going to have I to the 1, that's 1 higher, I to the 2, I to the 3, I replaced with 3, excuse me, Okay, so let's look at our next page, and at the top there are 3 more sums to write out. So I'd like you to do those, pause the video and see if you can write out what those are. For the second and the third ones, you notice there's this extra factor of -1 to the I and -1 to the I plus 1 out in front. So after you write out what the sum is, try to write another line where you simplify what each of those factors in front is, and we'll talk about that a little bit. So give those a try. If you get stuck, we'll go through them together. Okay, well, let's look at the top one together. This is a sum I equals 0 to 5 of 2 raised to the I. My lower limit is 0, so I'm going to start by replacing my I with 0, and we always go up by 1 for each term for our I value. So the next one would be 0 plus 1, so I would have 2 to the first, then 2 to the second, 2 to the third, 2 to the fourth, and then when I get to 2 to the fifth, I know to stop because now my I value is equal to the upper limit on my sum sign. Okay, let's try the second one together. Here I'm starting at a lower limit of 1, so I appears in 2 places in this function, and I just replace both of these i's with 1. So my first term would look like -1 to the first, and then it would be times 1 squared. And my next term, I replace I with the next higher number 2, so it would be -1 to the 2, and then it would be times 2 squared, and so on. So I would have a -1 to the 3 times 3 squared, a -1 to the 4 times 4 squared, and then now I'm reaching my upper limit of 5, so my last term is -1 to the 5th times 5 squared. Now I mentioned that these factors that are out in front actually simplify a little bit. For example, -1 to the first power is just -1. If we look at the factor in the second term, it's -1 now to an even power. It's -1 times -1, and so that will actually come out to be a factor of +1. When I do -1 to the third power, since I have an odd number of -1s multiplied together, I'll get back to -1 again. And so you notice that the factor that's out in front keeps flipping from -1 to +1. And what does that do to our terms? Well, if I multiply -1 times this 1 squared factor, I get -1 squared. And if I multiply +1 times this 2 squared factor, I get +2 squared. And here I will get a -3 squared. Here I'll get a positive 4 squared, and here I will get a negative 5 squared. So I included this example because it's an example of what's called an alternating series. It's terms whose signs are alternating, a negative term, then we add on a positive term, then we add on a negative term, positive, negative, and so on. So it comes up a lot in sums that you will see later on in Math 193 in your second semester of calculus. Okay. Let's look at this last sum. I'm going from I equal 1 to 5 again, so it looks just like this sum. And I still have an I squared as my second factor. The only thing that's different is that instead of negative 1 to the I have a negative 1 to the I plus 1. And let's see what that does to my terms that are over here. So the first term would again look like negative 1, but instead of raising it to the first power, when I let I equal 1, I'll get a 1 plus 1, or the second power there. Here my I is still equal to 1, and so I would get negative 1 to the 1 plus 1, that'd be 2, times 1 squared. My next term, I'm going to have negative 1. Now my I is equal to 2, so notice I'll have 2 plus 1 would be 3 here, times the 2 squared. And the third term would be negative 1 to the 4 times 3 squared. Then I would have negative 1 to the 5 times 4 squared. And my last term would be negative 1 to the 6. You notice when I equals 5, I have 5 plus 1 is 6, times my I squared would be 5 squared. Well, you notice that the same type of thing happens as happened in the example above. In other words, these factors out in front are either 1 or negative 1, but because I'm starting with negative 1 to the second power, instead of starting with a factor of negative 1 like I did up here, that would come out to be a factor of positive 1. And it would be the next one, negative 1 to the 3, that's equal to negative 1. And negative 1 to the 4 will be positive 1, negative 1 to the 5 will be negative 1, and negative 1 to the 6 will be back to a positive 1 again. So if we were to write these out, well, this would be positive 1 times 1 squared, so I start with positive 1 squared, whereas in the previous example I started with negative 1 squared. And the next term is going to be a negative 2 squared, whereas in the last example it was a positive 2 squared. The next one is going to be a positive 3 squared, and then a negative 4 squared, and then a positive 5 squared. This answer, let me kind of put a green arrow there. This answer looks almost like what we had up here, but notice that the alternating signs start at a different place. Instead of starting with a negative term and then being negative, positive, negative, positive, negative, we start with a positive term, so we have positive, negative, positive, negative, positive. So it just starts the signs alternating at a different place when we change this exponent from an I to one higher, an I plus 1. So I just wanted you to see the effect of changing the exponent here and how that changes where the alternating signs, what they begin with, whether they start with a negative or a positive. All right, what I would like us to do next is to talk about kind of going in the opposite direction. We've got a string of terms and we are asked to write them in sigma notation. This is a little bit harder because we have to identify what the function is that's common to all of these terms, and then we just identify where our I is going to start and where our I is going to end. So these terms are going to be some kind of a sum. And what you want to notice is they're all numbers raised to the 5th power. It's 1 to the 5th, 2 to the 5th, and so on up to 6 to the 5th. So all of these look like the function I to the 5th power, evaluated for different values of I. And where should my lower limit be? Where should my I begin? I should begin at the value of 1 and it should end at the value of 6. And you can just check in your mind, oh yeah, if I replace I with 1, I'd get the first term 1 to the 5th. And when I go to I equal 2, I'd get 2 to the 5th, and so on. Up to my upper limit, I equals 6, I get 6 to the 5th. So that looks correct. So that's the way to write this long sum in a nice compact notation by using this sigma notation. Why don't you try these 3? The last 2 are a little tricky. Well, the last one, I should say, is a little tricky because it has alternating signs in it. So you might think about the effect of this -1 to the I or -1 to the I plus 1 and how that gave us alternating signs, and see if you can figure out how to make this come out with alternating signs simply by writing it in the correct sigma notation with the correct factor out in front. So stop the video and try that, and then if you get stuck on anything, just restart the video and we will go through it together. Okay, well, let's try the second one. You want to just sort of notice that there's a pattern here. We have 4 times 1, 4 times 2, 4 times 3. I haven't even written all the terms here, but when we put a dot, 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 we are indicating that it goes on in the same sort of pattern, and the pattern should be clear enough. We should give enough terms that the pattern is clear enough that you can tell what that pattern is. And so there are terms missing here. That's what's indicated by the dot, 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 just like when we were adding n rectangles together and we put a dot, dot, dot in our sum. And then the last term is 4 times 15. So let's think about what our function would have to be. Well, it's 4 times something. So I'm going to write 4 times I. That would be the function that I'm evaluating for different values of I. I equal 1, 2, 3, and so on, up to 15. So our beginning I value, our lower limit on our sum, would be 1. Then it goes up by 1 each time until I get to the upper limit of 15. Sorry, I didn't give us a lot of room there. So it would be the sum I equals 1 to 15 of 4I, that function. Okay, let's go ahead and see if we can do this one. Here, I haven't actually kind of told you exactly what the different I values are. I'm making you work a little bit harder. You have to actually figure out the pattern yourself. And so let's think about it a little bit. It's 2 plus 4 plus 8 plus 16 plus 32. Well, somehow we want to write it in a way that we have numbers that are going up by 1 each time, like they were here, 1, 2, 3, and so on. Or here, 1, 2, 3, and so on, and some function was being evaluated for those. Well, I do notice that these are doubling each time, meaning that these are really powers of 2. For example, and I'll write it in another color so that we can see it, 2 could be written as 2 to the first power, and 4 could be written as 2 to the second power. 8 could be written as 2 to the third power, and so on. So in this case, they're making us work a little bit to figure out this pattern, and luckily 32 is 2 to the 5th power. So if I wanted to write this one in sigma notation, let's see if we can do it. I'm going to move it down here a little because I don't quite have room, and we'll do this one down below. So for this one, it's going to be the sum. What do my i's start and end at? Well, they're the exponents on the 2. They're starting at a lower limit of 1 and ending at an upper limit of 5. And what's the function that should go in here? Well, it's 2 to the first, 2 to the second. These are my I values that are up in the exponent, so it would be the function 2 raised to the ith power. So that's how we would write this sum in sigma notation. Well, let's look at this last example I asked you to do, 2 minus 4 plus 8 minus 16 plus 32. Well, these still look like 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and 2 to the fifth, but I notice that the signs are not alternating. It's plus, minus, plus, minus, plus. And so if I'm going to write out this sum, I want to have something that looks pretty much like what I did for the last example, but I'll need an extra factor in front of this 2 to the I to include this alternating sign, to give these terms these alternating signs. So I'm going to use a trick like we had up here, where I do either -1 to the I or -1 to the I plus 1, depending on whether I want my first term to begin with a negative or a positive. So this one here should be, see if I can give myself a little bit more room. This one should look just like this one, except that I will need a factor in front of the 2 to the I. So I'm either going to need a -1 to the I, or I may need a -1 to the I plus 1 here. Let's try -1 to the I and see if it gives me the right sign for the first term. If it doesn't, I can always add 1, and we saw that that had the effect of changing what sign the alternating signs begin with. So if I go ahead and evaluate this at the lower limit, I equals 1, the very first term I would get would be -1 to the first times 2 to the first. So would that be right? Well, let's see, the 2 is fine, but -1 to the first would actually be -2. We wanted to start with a +2. The only way to fix this up is to put a +1 up on my exponent on the -1 here. So we're looking more at something that looks like this, and you notice this started with a positive term here. So if I made this I plus 1, then when I let I equal 1, the lower limit, instead of having -1 to the 1, I'd have -1 to the 1 plus 1, i.e. -1 to the 2. -1 squared would be a +1, and I'd still have times 2 to my I value, which is 1, so I would end up with a +2. So check that out by writing this out yourself for the first few terms, and check yourself that you will get a +2 for your first term, you'll get a -4 for your second term, then it'll flip to +8, -16, and +32. But we can always put either a -1 to the I, that's what I usually try first, and then if that doesn't give me the right sign, I add 1 to the exponent and do a -1 to the I plus 1, and that exactly offsets by one term where our positives and negatives end up. Okay, well, I do want us to make a remark before we go on. So let's look at this remark right here. If I gave you this sum, I equal 2 to 5 of I squared, what would that be equal to if we wrote out the terms? Well, I would start with my lower limit of 2. So I replace I with 2, and my first term would be 2 squared. I go up by 1, so my next term would be 3 squared. And then I would have 4 squared, and I would end at the upper limit of 5 squared. All right? Now I want us to look at the sum that's right below it. And you may notice that it looks identical to this one. What's the difference? The only difference is that instead of an I for my letter here, by the way, I is referred to as the index. That's why we often use I for it. That's the index on the sum. I don't think I said that on the last page. The only thing that's different is that the index that I'm using, the letter I'm using for the index is different. Here I have a K, here I have an I, here I have an I squared, here I have a K squared. Now if we start to evaluate this by starting with K equals 2, well, the first thing I would have would be 2 squared. That pen doesn't want to work, 2 squared. And then it goes up by 1, so the next term would be 3 squared, 4 squared, and 5 squared. Is the sum that I end up getting any different? It really doesn't matter. These two things are exactly equal to each other. We get exactly the same string of terms to add together, so when we add them up, they'll give us exactly the same sum. The only thing that's different was that we had a different letter for the index. So it doesn't really matter what letter you use for the index. If I change this to a W equals 2 to 5 and I had a W squared, I would get exactly the same 4 terms over here when I go ahead and evaluate that summation notation. So we often say that the index is what's referred to, I'll say, is a dummy variable. And dummy doesn't mean it's stupid or something like that. It's more like a crash test dummy in a car commercial or something like that, where the dummy sort of stands for the person and the dummies are all interchangeable. It doesn't really matter which crash test dummy you put in the driver's seat and when you slam the car in some kind of test to see how well the car does or doesn't do in a test crash type situation. It's a dummy variable in that sense, that these letters are interchangeable, or the dummy sort of replaces or stands for something, and it doesn't matter whether I use an I or a K. And so it's referred to as a dummy variable, and the idea is that it doesn't matter what variable you use. Once you evaluate it, you get exactly the same answer. So that's something also that will come up often in second semester calculus. You'll do a portion of the course that's on sequences and series, and you'll talk again about dummy variables. Okay, this last one, I'm not sure why I put this example down at the bottom, but let's just do it. Oh, yeah, I see. Because it is slightly different than the ones that we did up here, because I'm going from 1 up to, and instead of having a specific number here, I have an n. So why don't you pause the video and see if you can write this one in summation notation, where your last term is not a number, a specific number, but think of n as if it were a constant. So your last term is 1 over n. Take a moment to try that, and then we'll go through it together. Okay, well, let's think about the function that's going on here first. I could write 1 as 1 over 1, and that way we can see it's 1 over 1, 1 over 2, 1 over 3, and so on up to 1 over n. So I'm going to use an I for my index, even though there's an n in this last term. I is the index, and the function that I'm evaluating in each of these terms looks like 1 over whatever my I value is. So I'm going to write my function is 1 over I. Now, what's my I going to run from and to? Well, I starts out at a value of 1. So my lower limit on my I, sorry, this is my slide number, just ignore that 15 there. My lower limit will be 1. That's where I want my I value to start. Then it goes up by 1 each time. I is 2, I is 3, I is 4, I is 5. There's a bunch of terms missing. I don't know how many because I don't know what n is. And what should my upper limit on this sum be? Well, my last term is 1 over n, so that's the last thing that I want to replace I with is an n. And so my upper limit is this unknown number n. If n happened to be 6, then my upper limit here would be 6, and I do 1 over 1, 1 over 2, 1 over 3, up to 1 over 6. But if it's some unknown number, it's still the upper limit, and I just let I run from 1 to n, do that sum of the 1 over i's. Okay, let's go ahead and use all this information that we've learned about sigma notation and try to apply it to those Riemann sums that we were talking about earlier in this section. So now what I'd like us to do is use this sigma notation that we've learned to rewrite our area formulas in a more compact way. So you might remember that R sub n was the sum of the areas of the right-hand rectangles, where we use the right-hand endpoint of each strip in order to figure out the height of the rectangle. So if you've forgotten what we did there, remember we had a function y equal f of x. We were looking at the interval from a to b. We divided it into n subintervals, and so we got n strips. Here's strip 1, strip 2, strip 3, and so on up to the nth strip. And for the right-hand rule, we looked at the first strip and chose the right-hand endpoint of that little subinterval from x0 up to x1, and that's what we used to create the height of our first approximating rectangle, and that's already been drawn for us. This is a picture of Rn for this particular function. So what is this height? This height is just going to be the function evaluated at this x value, x1. So that's what we had right here. F of x1 was this height of the first rectangle. Then we multiplied by the width of the first rectangle, which is delta x. And we did that for all n rectangles. Well, now I can write this in a nice compact form. So let's see if we can write this using our sigma notation. I notice that all of these terms look similar, but the only thing that's changed is this subscript here on the x. So I'm going to write this as f of something times delta x, and the something that goes in here is going to be x sub, and it's supposed to be x sub 1, then x sub 2, and so on up to x sub n. So I'm going to make a little subscript on my x and write x sub I. So my sum, I want the index then to be I, and what will the index run from and to? Well, I want it to start at a value of 1 and end up at a value of n, going up by 1 each time, x1, x2, x3, and so on. So I'll just write I equals 1 to n. We want the sum of f of x sub I times delta x, where I runs from 1 to n. And this is a much more compact way to write Rn. Also, we don't have to use these dots that we used, and that's considered a little bit unwieldy to have to put the dot in there. It's sort of indicating to the reader that they're supposed to continue this pattern in the same way, but this specifies exactly what that pattern is for all subscripts I from 1 to n. Well, let's try the same thing with L sub n. Remember, that was f of x 0 delta x, and the reason for that was that for the left-hand rule, we looked at this first strip, and instead of choosing the right-hand endpoint to evaluate the height, we chose the left-hand endpoint to evaluate the height. So the left-hand rectangle would actually be above the one that I've drawn here, which is for the right-hand rule. So notice that this height would be f evaluated at x0, and so that's the height of my first rectangle. I multiply by the width, which is still delta x, and then I move on to the second strip. Its left-hand endpoint is x1, so the height of the second one is f of x1, multiply by its width, and so on. When I get to the nth strip, remember we have to be a little careful with L sub n. For the nth strip, I have to choose the left-hand endpoint, which is actually x sub n minus 1. So when I figure out that height for the last strip, and I'm doing the left-hand rule, it would actually be f of x sub n minus 1. So the thing that goes in here would be x sub n minus 1. And now I can go ahead and write this in summation notation. Why don't you try to pause the video for a second and see if you can write this sum in summation notation using the sigma. Well, let's try this together. I'm going to go ahead and write my sigma symbol. I can see again it's going to be f of x sub, and the only thing that's changing in each term is the subscript on the x, so I'll make that my index. All of them have a times delta x, and so my I is going to run from, and now I want it to start at 0 and end at n minus 1. It's like we've shifted all of our subscripts to the left by 1. So I'm going to start at 0 and end at n minus 1. Okay, well, that means we can also write the exact area underneath here. Remember, we get the exact area from these approximations by just letting the number of rectangles n go to infinity. So to get the exact area, we could say, well, it's the limit as n goes to infinity of Rn, but what did we just say Rn is? We could write that in sigma notation. So it's the limit as n goes to infinity of I equal 1 to n of f of x sub I times delta x. And we could also, we said if this limit exists, and if f is continuous on the interval from a to b, this limit will exist, and it'll give us exactly the same thing as if we do the limit of the left-hand rectangles, the limit of L sub n as n goes to infinity. So I could write the area also as the limit as n goes to infinity of L sub n, but we've just got through saying that L sub n could be written using this new sigma notation, and it would be the limit as I runs from 0 to n minus 1 of f of x sub I times delta x. And just put a little remark down here, I think I just said it, but I'll just repeat it again. As long as f is continuous on this interval from a to b, both of these limits will exist and they'll be the same. So they'll be equal to each other and give us the same exact value for the area underneath the curve. Okay, well, let's go ahead and look at the other types of sums, Riemann sums, that we considered. Remember, we also, instead of using the left-hand endpoint on each strip or the right-hand endpoint on each strip, we said we could choose an arbitrary x value that we called x sub I star on each subinterval. And then we found the sum in that case, and we ended up, instead of with f of x sub 1, where that was the right-hand endpoint, we just called it f of x1 star. So just to remind you of what that xi star was, remember on our picture here that if we look, for example, at the first strip, we said, well, why do we have to choose the right-hand endpoint to create the height of our approximating rectangle? Or why do we have to choose the left-hand endpoint to create the height of our approximating rectangle? And in fact, we don't. We can be a little more lax, a little more general, and say, well, I'm going to choose any x1 star, and that could be any value from the left-hand endpoint up to the right-hand endpoint. And I'm going to create the height of my approximating rectangle by looking at the height under the curve at that x value, at x1 star. And so you got some other rectangle, but it was still an approximation for the exact area under the curve on that strip. So that's what the xi star values were. And so the height of my first rectangle is f of x1 star times its width, delta x, height of the second one, f of x2 star times delta x, and so on. Now we can write that in summation notation. So I could write that as the sum, and I'm gonna have all things of the same form here. I can see that these terms all look exactly the same except for the subscripts on the x stars. Here's x1 star, then I have x2 star, and so on up to xn star. So I'm going to put my index I as the subscript on my x star. So I'm going to do this sum of f of x sub I star times delta x as I runs from 1 up to a value of n. And so these two things will mean the same thing, but this is a lot more compact. So if I want the exact value of the area under the curve, I would then have to find the limit of this expression as n goes to infinity. So we'd say, oh, that's the limit as n goes to infinity of the sum from I equal 1 to n of f of x I star delta x. Is simply a more compact way to write what we wrote earlier in this section. Well, you might remember that we kept generalizing our Riemann sum until we got to the most general form of a Riemann sum. And this form, I should say right here, this form where we used an intermediate x value on each subinterval, the Rn and the Ln, were all special cases of the most general form of a Riemann sum. So Our most general form came when we also allowed the widths to be different. So instead of the widths of our rectangles all being the same, delta x, delta x, delta x, and so on, we said, oh, the first rectangle could have a width delta x1. The second rectangle could have a width that is different, delta x2. And so in general, the width of the ith rectangle, approximating rectangle, would be delta x sub I. So we allow our widths to be different, and then we got the most general form for a Riemann sum. And we said the sum looks like this: f of x1 star, we choose an arbitrary x value in each subinterval, times delta x1, the width of the first rectangle, and so on up to f of xn star times delta xn, where delta xn is the width of the nth rectangle. Now we can write that in our new sigma notation. So these also look like terms that are all the same. So each of these terms looks the same except for the subscript on the x's. And notice that in each term that subscript appears on the x star and also on the delta x. So when I write down what I need to put subscripts on, I put x sub I star and delta xi, since the delta xi, the delta x's now can be different. So now I just have to go ahead and decide what I runs from and to, so that when I write out this sum, I get what I have above. And I can see that my I starts at a value of 1. That'll make both of these factors of 1 for my first term. Then I will be 2, and that will give me this second term here when I replace both of these i's with a 2, and so on. The sigma tells me to add them all up, and I go up to a value of n again. So it would be I equal 1 to n of f of x I star times delta xi. That's a most general form for our Riemann sum. Well, let's go ahead and find the exact area then. In all the earlier ones, we were allowed to just let the number of rectangles go to infinity, but that was because they all had the same width. So as soon as you said the number of rectangles n goes to infinity, it meant that all of the rectangles had to keep getting skinnier and skinnier. The delta x had to go to 0. Remember, we had a little problem with the most general form of the Riemann sum, because it was possible to invent a scheme where the number of rectangles went to infinity, and yet not all the widths of the rectangles shrunk to 0. Well, how did we get around that? Instead of writing the limit as n, the number of rectangles, goes to infinity, we just insisted that the largest of all of our width sizes, which we called the maximum delta xi, we insisted that that shrunk to 0. So essentially, instead of saying the number of rectangles are going to infinity, we were just saying the rectangles themselves, they may be of different widths, but eventually I want all of those widths to shrink to 0. And then we just stick this abbreviated form of our Riemann sum in here. So I'm just going to repeat what I have up here, the sum from I equal 1 to n of f of x sub I star times delta x sub I. So we say the exact area is the limit as all of the widths go to 0, as the rectangles get skinnier and skinnier, of this sum, which is just this Riemann sum that we have written up here. Well, just to give you a little preview, in the next section, which is section 5.3, we are going to talk about a theorem that connects the ideas we saw back in 4.9, those ideas of antiderivatives, and indefinite integrals. We're going to connect that to the ideas that we've seen here in 5.1 of areas under a curve. I'll say areas under a curve. So it turns out that although these might seem like totally different ideas, there is an intimate connection between the two. And that's what will be coming up in the next video.